this computer. Okay, good evening, everybody. We here, it's week 8, I think. So let's just have a quick look. I've shared my screen. Can you see my screen?
Yep.
Okay, so there we are. We're in week 8, 4th of May, statistical inference and introduction. And then next week, we're going to do chapter 10 and 11. And next week is also another exam quiz that's starting. And I do apologize. I must still grade exam quiz 2. I'll hopefully do it in the next day or 2. So tonight we're going to look at statistical inference, which is chapter 9. But before I go there, I actually want to look with you at the assignment, which is so coming up. Let me just see. I'll make a note in your book. It's 2 weeks after next week's exam quiz. You have to hand in your assignment. And I'll show you what I've done. You've basically got, you can tell me now, you can tell me what needs to be in the assignment, because that's the idea. I decided in the end that we will look at the COVID-19 data, and I've actually given you the data set. Is the data set in here? Yeah, I've given you a version of the data set. Is that the one? Yeah. And I'll give you another one as well. And your assignment will be to analyze that data and basically produce a report. I'll show you, I'll talk you through the data a little bit and show you what I've done so far. Come on. Okay, I'm just going to put it here. Okay, I'm just starting up my stuff. Okay, let's see. You see there, I've given you a reference where I got it from, and the initial data set contained one worksheet, namely, and I'm going to show it to you just now. And I added some, in my case, and that's what the assignment will be, is you must choose 3 countries of your choice. In my case, I've chosen Austria, not Australia, Austria, Canada, and Botswana. And I deliberately did not choose Australia or other popular countries. I expect you to choose 3 countries that you are interested in, okay? I've added 2 columns. One is called cases per million and deaths per million. And this will allow me to compare different countries, taking into account different population size. Now, I don't know you, but it's quite frustrating when you hear so many thousands of people died in a country, and you've got no feel, is that terrible or is it not? And the reason you don't know if it's terrible or not is you don't know if the country is big or small. You know, 10,000 people dying in a country of 10,000 is terrible. 10,000 dying in a country with 1 billion people, obviously, each person dying is terrible, and if you're a family member, it's terrible. But in order for us, from an analytics point of view, to make sense, we want to know what proportion is it of the population. Does that make sense? And particularly, if you want to compare countries with each other, is Australia doing better than America? Well, if you don't consider the population size, you won't get anywhere. Okay, let me show you what I've done so far. You do still see my screen, don't you?
Yes, we so.
Okay, here's the raw data that you got originally, and it's got all the countries in the world is in there at the moment. Let me just unfilter it. Okay. I just want to, okay. So if I quickly want to see which countries is in here and population, country, and which ones has got the most deaths for, or okay. Okay, if I want to see quickly how which is all the countries that's in here, how will I do that?
Make a pivot table.
Yeah, I'll do a pivot table and I'll put the country on one side and sum the number of deaths, and that will give me. Okay, so as a quick summary, I can put the country and territories here, and I can put the number of cases here and the number of deaths here, and it gives me the sum anyway. So if I want to know which country has got the most deaths of all the countries in the world, I can just sort from largest to smallest, and instantly the United States of America, Italy, United Kingdom, Spain, France, Belgium, and so on. Does that make sense?
Yep.
And similar, if I just want to know the number of cases, I can again just click on sort, largest to smallest. I suggested you taking, for instance, interesting Qatar. They've got a case, but they've got very few deaths, relatively speaking. Yeah, Namibia. Okay, you need to choose 3 countries. So what did I do? Is I chose 3 countries. How do I choose them? Do you want to give me any 3 countries that you feel like? I'll show you how I did it. You click on data, you click on filter, and I can, for instance, choose Angola, Denmark.
Do the 3 countries that we choose have to have like dramatically different results?
Yeah, otherwise it will be difficult. You know, they all got the same results or similar. You want something that's interesting, isn't it?
Yep.
And you need to tell me, why is it interesting? Sharma, if you have to choose 3 countries, which 3 countries would you choose?
United States, New Zealand, Australia.
Okay, those are 3 good countries. Dariet, what would you choose?
I use America,
Yeah.
United Kingdom,
Yeah.
and Italy.
In Italy. Okay.
Yeah.
Now that's interesting. What would you choose, Brenda? Brenda there?
Do you have China as well?
Yeah, choose China. Brenda, which 3 countries would you choose to look at?
I'll probably choose Africa.
Africa is not a country, so South Africa. Maybe.
South Africa. Something like I'm not sure. Probably Italy, because I know they had a lot of cases, and probably the United States, but I'm not sure. That's
Okay,
just-
at any rate, I'm showing you to choose the three. If I'm
Oh,
wrong, just tell me. You
Yeah.
just go into data and filter it. And my recommendation is, in this case, I've now got Angola, Denmark, and Germany. Can you see? I've just got those three.
Yeah.
Then you highlight the rows like this. Control C, copy, and go and put it into another spreadsheet. Now you just got your three countries that you have to worry about. And you don't have to worry about all the countries, okay?
Yeah.
So in this case, I've now just got Angola. Okay, so what did I do next? I'm going to delete this now. In the three countries that I chose, which is Austria, Canada, and Botswana,
Yeah.
in these three countries, I now added some calculations on the right-hand side. Would you agree? So I added a calculation that says cases per million and deaths per million. And then I added another one, accumulated cases and accumulated deaths and accumulated cases per million and accumulated deaths per million. Can you see how, and there you can see what the formula is of, for instance, accumulated deaths is adding O2 plus F3, which is adding this number plus the new deaths. Can you see that?
So adding the deaths plus the death per million.
The deaths of the day before,
Yep.
plus the current day.
New deaths.
Yeah.
New deaths.
Okay, and then as you can see, okay, let's go to a place where it makes sense. For instance, here, I added 337, I added 13 to it, and that gives me the new total. What is extremely important is that this needs to be sorted by country and then by date to do this at the number. Okay. And then you need to figure out where the countries change. For instance, in this case, Austria changed to Botswana. And you here need to go and change the formula to just be equal and not add it up anymore. Otherwise, you add this country to the previous country, which is not what you want to do. Is that right? Do you understand that?
Yep.
And similar here, where it starts with Canada, I had to, that's why I have to go and change the formula so it just add up there. Okay, everybody happy with that? So the first thing that I want to do is have a little table that summarize those three countries for me. So how do I do that? Insert, in my view, a pivot table. Click on OK. And I want the country, and I want the okay, and I want the number of cases, the sum of all the cases, and I want the sum of all the deaths. I want the sum of all the cases per million and the sum of deaths per million. Can you see that this gives me quite a nice table as a summary? And in this case, we now see that Botswana had very few cases. And so Botswana is probably not going to be very interesting to me, but it's one of the countries I chose. Where Canada, and I can already see that in terms of deaths, Austria had less deaths per million people than Canada. So I can already write a little summary about this. Do you agree?
Yep.
So here's an, okay, and I can, come on. There's no reason to have decimal points, but because it's just, okay, no, there is for this. Okay, sorry about that. I'm going to add some decimal points here. Okay, so that's my first summary. What would be a next good summary, do you think? If you look at, here's my data, what would be another good summary? Obviously, I want to do two graphs, one that just, or two graphs that gives me the cases per day, the deaths per day, and the cases per million and the deaths per million, but also the accumulated cases per million and the accumulated cases per, and so on. Do you agree?
Yep.
How do I do that? I insert pivot table, because that's a very convenient way to do it. And I can include what I want is the date. And what I want is, for argument's sake, if I want to just draw the raw cases, I put that there. And I can do that for all the countries that I've got. Draw that there. I can ungroup this because I actually want the daily numbers. And if I now go and insert and actually draw a line graph, do you agree that this gives me a very quick summary? For instance, I can see Canada had no cases until the 1st of April, or 2nd of April. And Canada sort of had a few and then died, have a few. Austria jumped up, but can you see that their number of daily cases has already fallen down again?
So when we compare all three countries on a graph, do you prefer us to use a line chart?
If it's time, remember this is time, so this is a timeline chart. Okay, so what I also did, by the way, is I've removed all the places where there's 0 cases. So I highlighted this, I took this original data set here, and I highlighted all the places where cases is 0. Like this. Up to here, and I delete those lines. And similar, and this is for Austria, Botswana, there was no, that was 0, or in this data set, and similar for Canada, yeah, Botswana started off with 3. And Canada, I highlighted all the Canadian ones that were 0, like that, and deleted it. So, and then I started, and here's my case analysis. So here's the actual graph that I've drawn for my thing, and average cases per million. There's a nice summary graph, and here's one way where I compare it. Now this is the number of cases per day, but you've probably seen a lot of places where they analyze the number, the sort of growing number of cases. Let me see if I've done it here. In this particular case, and I started formatting this to the standard that I need in the report, this is the accumulated daily deaths per million. And here you can see Austria, Botswana, and Canada. And here is the daily number of cases for Austria, Botswana, and Canada, which I've now done already. Can you see the kind of analysis that I need you to do?
Mm.
Okay. Now, if I go to my Word document, okay, I will work further and I'll come up with your assignment. But the basic part of your assignment is use these data sets that I supplied to you. If you want to go and draw new ones, you're welcome, but I don't think you need to. You can use the ones I supplied to you. 1, 2, choose 3 countries and manipulate the data so that you can report on it. And then use the framework that I've given you on a previous round. Let me just see where that's. Forums. Wrong business analytics. Yeah, here we are. Oh, okay. I think it was in the other, in the discussion group. I'm going to get there sooner or later. Can you still see my screen?
Yeah.
Okay. Thinking about it. It's idling along. Forum. Okay. So you, man. Okay, so here's the layout of, so I'm going to copy this straight through here. Okay. And I'm going to stick it into a Word document.
Cool.
Okay. So the first thing I want is a cover page. And I'm just going to type here this Bus204 is sign and the date, May 20, created by so on. And I'm going to make this big because I want this as a cover page. 48, right? And I want a little picture in here, so I'm going to say insert picture. This device. And I can go to my camera roll. Oh. Where's my pictures? New pictures. Okay, that blockchain looks good. So there's my cover page. How do you like that, huh? Clever.
Hey, so Francois, is that all we got to add for the cover page? Because I know for other assessments we have to add like the subject code and like all that other stuff. Is this all we need to do for the cover page?
Or have both.
Mate, no, I'm just showing you a little example of what I would do. And yeah, by all means, you need to have the subject code and all of that stuff in, make it possible for me to know where it sits. Okay. So then I've got the executive summary, and I'm going to make that heading 2 and questions investigated about 5. Okay, so data sets and variables. I'm going to write something about so my executive summary, obviously I'm going to write that later on. Questions. Okay, so I'm going to say chosen 3 countries, namely, in my case, Austria, Botswana. What was the 3rd country that I chose? In Canada. I chose them because, and then I can write a whole list. If I really have to choose a country, I'll choose Sweden, because what do you know about Sweden and the COVID-19? Have you know anything about them? Do you guys read about the COVID-19 a little bit? Watching news and so on? The interesting thing about Sweden is they've decided to do nothing. And the whole world is heavily critical of them. And yes, they do have quite a high death rate. But at the same time, their economy goes on, their universities are open, and people go to restaurants and eat and drive around and go on holiday, and their economy just carries on. Interesting, eh?
Yeah.
Okay, and then, okay, so that's on a page. Then I'm going to go to a new page. New page. What was the data set and variables? Now, as it turned out, you can write something about the data set. I chose blah, 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 data set from blah, 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 blah. Where did you get it? The variables, these, and here's all the variables. Okay, and I added the following calculated columns. Here's the columns that I added. Okay, why did I add the columns? I just explained to you that if you want to compare countries with each other, you should divide it by the size of the country. Okay, so give you a little bit of an explanation. Why did you add? And you might add other columns if you want to. Doesn't matter. Okay, then summary statistics, control enter. And you've seen me done some of that already. Where was it? Was it sheet one? No. Okay, let me. One thing I thought to myself. Where was it? Sheet 5, sheet 3. Yeah. Yes, some summary statistics. So I'm going to stick that into my Word document. Overall, discussion. Is this helpful for you or not really?
No, this is really helpful. Yeah.
That's right.
Discussion. Canada have the most deaths per 1 million people, while Botswana have almost none. And then have a discussion. It does beg the question, one is if Botswana is identifying COVID-19 cases at all or correctly. They might be completely oblivious of the rest of the world. I don't know. I mean, if you imagine if it's possibly a small country or a country that they just don't test for cases, so they're unaware that it is there. Okay, so then we've got, okay, and then I can go question 1. What kind of analysis do I propose? Summary of cases for the 3 countries. Okay, and then I can put in the result is, and I can decide I'm going to do those 2 graphs, one of the cumulative number, summary of, okay, just to make my life easier, I'm going to say deaths for the 3 countries. What's the result? How are we doing for time? Yeah. Results, and I can go to my spreadsheet, and I can go deaths analysis. Copy into my Word document. Paste picture. Make it smaller. here's my discussion. But I might want to bring in that other graph, and here I'll show you a quick trick. If I go right click here, I can say save as template. COVID analysis, save. Yes. And now I can go to this one, and I can right click and say change chart type. Go choose from a template. COVID analysis. Click on OK. And you see here it instantly changed my thing with all the correct backgrounds and everything. Quite pretty cool, huh? And this is cumulative deaths. This is date, and this is number of deaths. Okay, Control C, take it to here. Control V, no, shouldn't have done that. Okay, and now I can clearly see this discussion. What can I see on this graph? What can you guys see? Austria,
Botswana, Canada.
Seems to gone past its peak, while Canada is still growing.
Is there anything else that we can add to get more marks on that?
Yeah, you can add a lot of stuff. You need to have a little paragraph here. I'm just giving you little pointers for where you're going to go. Yeah, no.
So how many words per discussion would you want?
A paragraph for discussion, and you tell me, what do you think is fair?
Probably like 150?
One word? Yeah. One of the conclusions is is not really testing or free from the virus. Okay, I expect about 10 pages.
Yeah.
Okay, excluding the cover page and so on. So 10 pages, and I expect, you know, if this is one analysis, question one, I need about, I'd say 3 or 4 of this type of thing. Okay. Does that make sense?
Yep.
But I'll continue with this document and publish it as I carry on. That you guys
Oh, great.
get a feel for what I'm interested in. How do you feel? Would you be able to do this? Okay. How many hours do I think you should spend on doing it? Between 6 and 8 hours. Up to now, I've already spent 2 hours. Now, I've saved you probably an hour finding out where the data is and downloading it and so on. And I'm giving you clear direction on what I expect. I probably spent 3 hours now, up to now doing this. But I've now got a clear view. So to go back here, questions investigated. I chose them because, okay, so question 1. How do the 3 countries compare over time in terms of deaths? Okay. Question 2, I'm now defining the questions I'm going to look at. Question 2, how do the 3 countries compare over time in terms of cases? In terms of cases. Question 3, and maybe I'll make this question 2 and this one 3. And summary of summary descriptive question 1. Question 1. Descriptive statistics regarding deaths and cases. So, and you know, descriptive statistics, it's the mean, the min, the max, the standard deviation is the standard deviation, the range, the 25th percentile, the 75th percentile, and the
Interquartile.
Interquartile range. Okay, so that's question 1. I'm even going to make this question 3, question 4, and question 2. Question 2, histogram of deaths, cases per country. Okay, and okay, so there we've question. What can we do for question 5? What do you think? Well, this is plenty of work, because if you look at this is actually descriptive statistics regarding deaths and cases. So this is actually question 1. This is already 2. Okay, and this, if you look at this is 2. Each of these are 2 already. Two reports, because no, this is 1. Yeah, and this is 1. And I might make it prescriptive and say this is what you've got to do. Would you like me to demonstrate how I would do this first one?
Yes, please.
You're always so eager. Now, the reason I'm demonstrating this is you'll see there's a lot of what one would call data wrangling. Um, so, okay. So, for instance, for that one, I need to have the cases removed. Can you see that? So, what I would do and what I will do now, demo, is to do the summary move or copy. So I'm making a copy of this particular one. And I'm now just going to focus on cases. So I don't need to have anything to do with that. Delete. Come on. Okay. I don't need deaths because I'm just going to look at cases. Delete. Okay, Control Z. You first need to cut and paste these and remove the fact that it's a formula. And how do I do that? I paste the numbers. Okay, now I can remember that delete the deaths, delete deaths. And I want the cases per million. I don't want the deaths. And I want the and for this particular part, I won't need the cumulative numbers. Okay. Now I can. Okay, what I would do is let me just think. How would I set it up to be simple? Okay, I would cut and paste Botswana out. Where's Canada? Botswana. Control X and put it next to here. You'll see the method in my madness just now. Maybe you'll never see it, but anyway. I want, okay, and then I want to, and I want Canada next to it. This is one way of doing it, and I think it's the easiest way of doing it, but you might differ in your view. Okay, so the date is not important to me anymore. Delete. This is cases Austria. Okay, I'm going to make it significantly simpler now, and I'm going to remove, say, we're just going to look at cases. And I'm not going to look, this is cases Austria, and I'm not going to look at any of this other stuff. And you'll see just now why, and this is cases Botswana. And I delete all this up to there. Okay, and this is cases Canada. And I can delete the rest. Okay, now I insert here. Okay, right. And now I can, okay, I want to just delete all of this lot. Don't know what this is, but I'll delete it. Okay, now I can go on top here, insert, and I now can create my little table that says, okay, mean, min, max, range, standard deviation, 25th percentile, median, boring, huh? 75th.
Oh, this is good. This is real good.
Okay. Now I can fill in my formulas equal average. Misname, NOMA. Okay, average. Right. The min. I just want to check something if I. Yeah. Okay, so I didn't need to do that. So let's just do it back. Okay. Right. And so now to do the min, I'm just going to Control C, V, min. So all of them should be, the minimum should be 0. Yeah, I was right. We change that to the max. Okay. The range equal this minus that, which will be the same for everyone. Okay, standard deviation is equal STDEV. Okay, 25th percentile is equal percentile. Percentile, the array. Percentile, and this is the 25th one, comma 0.25. Okay. That right? Okay, you say so. Again, this one I can, the median is the same as the percentile 0.5, isn't it? So I can just copy this one there. And instead of 0.25, I'm just going to make it 0.5. Okay, and the 75th percentile is the same story. Okay, interquartile range, quartile range is equal this minus that. Okay, now I can measure, and this is Austria, and this is Botswana, and this is Canada. I can format this nicely. Tick outside borders, all borders, tick outside borders, and make that bold. This bold. If I want to be fancy, I can insert a table. View. This view. Okay, there's all kinds of ways of how I can make this looking very snazzy. But one thing I do want to do is convert all these values to 2 decimal places like that. Control C. I go back to my Word document. So here's question 1. Well, okay, question 1. I'm just going to stick it in here for the moment. Control C. Question 1. Control V. So now I can, this is obviously the results. And then what do I want? I want a discussion and conclusion. Conclusion. Clearly still need to do. So up here when I've now got this. So there's my question 1. So let me have a quick discussion on here. Results. Discussion. Canada have the most case. Is this deaths or was this cases? No, cases. The highest. Cases day at 594, 595, 595. Botswana is the lowest at less than 1 case on the average. so which one has got the biggest, which one has got the interquartile range? Canada varies the most. Canada. This. The interquartile range is 167. Conclusion, as this is time related data is not says with caution. Okay, how do you like that?
Yeah.
So there I've done question 1, and I can make it heading 3, and I can put it on its own page. Enter. There's my first one done.
You know how you put the borders on that descriptive statistics table?
Yeah.
Can you do the same for the pivot table that you put up? Is it?
What? Sorry.
You know, you put the borders around the descriptive statistics.
Yeah.
So we see, yeah, right there. You know, it's.
Yeah.
Is there a way to put borders around that pivot table?
Which pivot table?
Back in your Word document.
Okay, let me just see where I've done it. Yeah, I can't. Sheet 5. This one. Okay. What I personally would do is I would cut and paste this and paste it just the numbers, and then yeah. Thanks for pointing it out. Countries, number of cases. Total deaths. Total cases. So it's important when you produce a report that you think of the headings and so on, total number of deaths. Okay, and then you can go like this and wrap text, yeah, and then go all borders, tick border, Control-C. Okay. That makes sense? Yeah, so every step of the
Yeah.
way, you need to think how it will look in a report. You need to be consistent and readable and good titles and so on. And I'm now thinking one will have to go back. Does this total number of cases per million, does it actually make sense? I think it does make sense, but one will have to think about it. And maybe you want to format it differently so it haven't got that many decimal places. So let me quickly go and do that. This is,
Did you wanted it round down to the second decimal?
I did already. I've done that. You and me are on the same page, mate. There, 2 decimals. Okay. Okay, I think, sure, we've gone 15 minutes over with this one. Okay, but you get the idea. This is the assignment.
Yeah.
Okay, can we take 6:45? What time? Yeah. Can we have a 5-minute break? Then I'll be back.
Yep.
Okay. So now. Okay. I'll quickly had some dinner, so thank you. At least the people that listen to the recording, they can fast forward through the breaks and so on. I forgot to pause it. Anyway, let's carry on. Analytics. Okay, tonight we're actually going to look at statistical inference. Now, it's a relatively complex. Are you guys back and can you hear me? Can somebody confirm that you guys are here there? So it's chapter 9 in the book. Let me see if I can. Just want to bring up my PowerPoint slides. Chapter 9 in the book. And it's about right from the beginning up to now, we've not really dealt with samples. We've always analyzed the total population. Now we're going to look at, in the end, in real life, we often are not able to measure the total population. We can only measure a sample. And from that sample, we want to draw a conclusion. And in many cases, even if we get to measure everything, like in this COVID-19 data sets that we've got, we theoretically measured everything. We then typically want to say something going forward or in the future. So again, you can consider everything that happened up to now was a sample, and we actually, the whole population is everything that's also going to happen in the future. So we sometimes have to also use, even if we think we've got everything, we still want to say this is actually just a sample. So I'm going to share my screen again, and then we're going through the slides. So chapter 9 is about statistical inference. Can you guys see my screen?
Yep.
I'm just moving us all out of place. Okay. And in this particular chapter, we want to understand again data types. How many data types do we have?
3 types.
Yeah. And can you tell me what they are?
Yep. Numerical, nominal, and the ordinal.
Okay, you've got it. And we're going to look at primarily numeric data. And we're going to look at, if we take a sample, so here's a population with 1,000 people in it, and we just draw 100 out of it, and we calculate the mean or the average. How does that compare to the whole population? And similar, if we draw a sample, a proportion, so if it's nominal data, you can draw, and you want to estimate how many black colors are there, or how many yellow socks are there, or so on, which is a nominal type of data. You want to look at the sample proportions and how does that compare to the whole population. Okay, so we're going to look at what the importance of statistical inference is, explain why we use it, and then there's a big thing called the central limit theorem and the properties. And you'll see now also why I've always said the normal distribution is the most important distribution, and you can almost forget the others, but normal distribution you've got to know. And you'll see that's all related to the law of, what was it? The law of big numbers or something. The central limit theorem. Central limit theorem. Okay. The process of drawing conclusions about the property of a population is called statistical inference. So if we want to estimate the mean annual income for Brisbane, we can draw a sample, calculate the mean, and say, okay, that's for the whole of Brisbane. Another way is, we say, for instance, we want to estimate whether fuel additive is successful, yes or no. We can we have 10 cars where we add the fuel additive and 10 cars which we don't add it, and then calculate the average kilometers, and from that draw an inference of all of it. Okay, so recall from chapter 1, we've got parameters. That is when we talk of a population. Population have parameters, and a sample have statistics. So whenever we talk about statistics, we mean it's something that comes out of a sample. But if we talk of a population, we normally have parameters. In many applications of statistical inference, we draw conclusions. Okay. Data type, the type of data being measured, we've already dealt with that a little bit. The problem objective is, what do I want to show, or what do I want to prove? If you look at your assignment, you need to define the objective, or another way to say is, what is the question that I want to answer? Okay, there's our data types, numerical, nominal. You can see they're not talking of ordinal much anymore. And I've added another type, which I say is time related. And I still think it's worth analyzing time differently from any of these ones. You will find that every statistical method has some specific objective. And for the rest of this time, we're going to look at this every night, every lecture, we're going to look at one more. How to describe a single population, how to compare two populations, how to compare two or more populations, analyze relationship between two variables. Can you remember that one? How do we do that? With a scatter chart or an XY chart, remember?
Yeah.
Analyze the relationship among two or more variables. So these are all things that you know, but up to now we've done it for a population and not for a sample. Now we're going to do it for a sample and then draw a conclusion for the population. And that's called inference. A systematic approach to this statistical inference, a summary. Okay, from here onwards, a number of techniques of inferential statistics will be introduced. It's also important to decide how, when, and why a selected technique should be used. So you've seen in the assignment now, we want to know how are we going to analyze it, what technique are we going to use. So you've seen that for me, the most important technique is line charts, but we can also use descriptive statistics. And why do we use it? Well, it's most suitable for that specific type of data that we've got. Okay. If we describe a single population, that's chapter 10 and 12 and 14. And for numerical data, we're mainly going to focus on numerical data now. But and this is a nice table of where, if you in future have to do something, we want to analyze the relationship. We're going to look at chapter 17, 18, and 19, and so on. We probably will only look at chapter 17, and we'll probably only look at chapter 15, and so on. Okay, in real life, calculating the parameters of a population is prohibitive. Why? Because populations are very large. Rather than investigating the whole population, we take a sample and then we calculate the statistic that relate to the parameter. A sampling distribution of the statistic is a tool that tells us how close the statistic is. Okay, so what do we want to do? We want to measure something. We want to measure say the ability of children to read and write. We want to measure that. Now we can't go and measure it for everybody. So we're just going to draw a sample of children, measure their ability, and then calculate the average and say, we estimate that the average for the whole population is this one. But then we need to do something important and say, how sure are we that we're right? And this is where the distribution come in. We need to look at the distribution. Okay. The sampling distribution comes from sampling, and the method we will employ is use the rules of probability. Can you remember the rules of probability? And the laws of expected value and variance. Expected value, whenever you see expected value, think mean or average. And whenever you read variance, think of variance, standard deviation.
Yeah.
Okay, then they use an example here. A fair dice, I think it should be dice, is thrown infinitely many times with a random variable. X is the number of spots showing on any throw. Probability distribution. You remember probability distribution? If you throw a dice to get a 1, what's the probability? 1 over 6.
1 out of 6.
And 2 and so on. And the mean and variance are calculated as follows. So we can calculate the mean, because this is a parameter for the population. And if you do, 1 times a 6 plus 2 times a 6, 3 times a 6, 4, and so on, you get 3.5. So we know if we throw a dice a lot of times, the average or the mean will be 3.5. What can we say about the standard deviation? Now, here's a formula that you can apply, and it comes up by 2.92. And this is the variance, sigma square. And sigma, just on its own, is the standard deviation, 1.71. What does it tell me? It says to me that this 3.5, most likely, the numbers will be, okay, this is actually a uniform distribution, so it's not as neat or as nice as a normal distribution. But for the moment, just sort of accept that. If we, on the other hand, throw 2 dice, so we can get a 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, and so on, 3, and the average between the two, for instance, 2 and 5, the average between 2 and 5 is 3.5, right?
Yeah.
And we can draw another, so these are all possibilities. There's 36 possible samples of size 2. there are only 11 values for X, and some occur more frequently than others. Can you see that the 4 and 3 and 3 and 4 occurs more, or the value 3.5 occurs once, twice, 3, 4 times. Out of the 36, 3.5 occurs 4 times, where 1, that value of 1 only occurs that once.
Mhm.
So if I draw a histogram of all those values, can you see that this sort of looks like it's normally distributed? Because the 3.5 occurs 6 times, and the 1 only occur 1 out of the 36, and the 6 occur only 1 over the 36. Do any of you play games? My wife likes a game called Settlers of Catan. And there you've got 2 dice, and you see this pattern quite frequently. Okay, if we compare it with our first example, which was 1, 2, 3, 4, 5, and 6, with a sampling distribution of X's, where we have a sample of 2, can you see that this one is the whole population, and this is, if we draw a lot of samples of 2, this is the population. Can you remember when we calculate the average or the mean here, it was 3.5, and guess what we're going to get here? It's also 3.5. So the average is the same as the population mean, and the standard deviation is that divided by 2. How many were in each sample? 2 dice. So it's divided by n. Okay. So that's sort of a broad thing, but if we want to do it for any number of things, we can. You draw the sample, calculate the average, and you say, right, this is my estimation for this sample parameter. You calculated out of the sample the variance or the standard deviation, but you divide it by n, by the number of that's in the sample. And that will give you the population parameter, an estimation of the population parameter. And by the way, this is called standard error and not standard deviation. So there's a lot of terminology between this inference, but don't worry too much about it. Okay, now here's the central limit theorem. If a population is normal, then we know that the sampling average is also normally distributed. And then the key thing here is, regardless of what the initial population looked like, if you draw more than 30, it will also be normally distributed. And that's why normal distribution is basically that important. Because regardless of what it comes from, and this is called the central limit theorem. I hope to give you a demonstration of that a little bit later. And the larger the sample size, the more closely it will be normally distributed. Okay, it's just quite confusing to you, but the sample mean of a sample is the same, or is a good estimation of the population mean. The sample variation divided by the number of items in the sample is a good estimation of the variation of the population. If X is normal, X is normal. If X is non-normal, X is approximately normally distributed for a sufficiently large sample. So the rule of thumb, if you draw a sample, if somebody say, go and measure the size of the fish in the dam, how many fish must you catch? More than 30. Try and catch more than 30, because then you know the distribution is normal. Here's examples. Hopefully the picture depicts it. Let's see if I can blow it up a bit. Yeah. We start off, can you see n equals 5?
Yeah.
And you can see what the distribution is for the die. It's the same, that same dice that we threw before. And instead of throwing 2 dice, we're throwing 5 dice. Then the average will look like this. Can you see it's again centered around 3.5. If we throw 10 dice, it's becoming narrower. Can you see that the spread is less?
So the higher, the more narrow.
Yeah, because can you see here where I estimate the variance, I divided by 10, where in the first place I divided by 5.
Yep.
And if I put even 25 dice, you can see this becomes very narrow because I divide by 25. Okay. So now we're going to tap into the fact that this is normally distributed. Standardize it. You remember how you standardize a normal distribution? You take the mu, which is the parameter, population parameter, and you take the average of the sample, and you subtract that, and you take the standard deviation and divide it by the square root of n. And that gives you Z, which we now know is normally 0, 1, N01 distributed. Okay. Forget this for the moment. There's a correction factor. If n is very small, you can do some correction, but forget that for the moment. Sampling distribution of the sample mean. If the population size is large relative to the sample size, the finite, okay, that's the correction factor, so forget that. Example 1. The weight of each 32-gram chocolate bar is normally distributed with a mean of that and the standard deviation of that. So if you produce chocolate bars, and I worked for an organization which in fact produced apples, and they need to put a box of apples and they need to say how much does each apple weigh. So for them it was a big deal. So they say the standard deviation is 0.3 grams and the mean is 32.2 grams. Do you understand that? Find the probability that if a customer buy 1 chocolate bar, that bar will weigh more than 32 grams. Find the probability if a customer buy a pack of 4 bars, the mean weight of the bars will be more than 32 grams. So in the first case, we've got a sample of 1, and in the second case, we've got a sample of 4. Now let me do my, okay, I'm first going to talk you through how they've done it sort of manually, and then we're going to do this in Excel. Is that okay?
Yep.
Yep.
You cold, buddy?
Okay. Let's see. Find the probability that if a customer buy 1 chocolate bar, that bar will weigh more than 32 grams. The random variable X is the weight of the chocolate bar, which is normally distributed with blah, blah, blah. So the probability, and here they normalize the thing, which we don't need to do. So what we want to do is estimate the value that's shaded here. Can you see that? Okay, so let me jump into Excel and see if we can get the same result, much simpler. Won't that be cool? Here's the problem. Okay. Now, what was the important thing that I said? Whenever you deal with this type of problem, draw the picture. And I frequently demonstrated to you how I draw the picture. Now, where is this? Shapes. Pictures. No. I use that one. So I draw my normal distribution. Okay. What a cool normal distribution, man. I'm proud of that normal distribution. And here's my x-axis, and here's my, right? So the mean is 32.2. Can you see there? It says there 32.2. 32.2. Okay. And the standard deviation is 0.3, and I told you that 3 standard deviations is about there. So, so that is equal 32.2 plus 3 times 0.3. There's something wrong. Okay, so that is 31, and around here we'll have equal 32.2 minus 3 times the standard deviation, which is 0.3. Can you see what this now look like? Find the probability by 1 chocolate bar. That bar will weigh more than 32 grams. So this is 32. So the area we are interested in is this area here. Illustrations, shapes. Okay. And we know within Excel we can easily calculate this area around here. So that is 1 minus, this will give me 1 minus this area, isn't it? Because we know the total under this curve is 1. So let's try that. Normal distribution. My x that I want to calculate is 32. My mean is 32.2. The standard deviation that I'm interested in is 0.3. And I think let's try true. Okay, first of all, we know this will be less than 0.5 because 0.5 is half of this curve. So we know this will be less than 0.5. So let's see what the answer is. Yep, that's right. So what I now need to do is to calculate this area is this one minus. So it's 1 minus that. So the answer that I get is 0.74. The probability that somebody buy chocolate and it weighs more than 32 grams is 74%. Let's see what the answer is that they got. I hope I'm right. Yep, 7.7486. Can you see I didn't need to go through all this rubbish because I can just use Excel.
Yeah.
Did you follow what's going on? I mean, I scarcely follow what's going on. Okay, so let's go and look at the next question. The next question is, find the probability that if a customer buys a pack of 4 bars, the mean weight of the bars will be more than 32 grams. Okay, so let's look at the solution here. Find the probability that if a customer buys a pack of 4 bars, the random variable of interest is the mean weight per chocolate bar. The population X is normally distributed with that and that. Therefore, X is normal with the same value, 32.2. But in this case, this becomes 0.3 divided by the square root of 4. Remember, because we're now buying 4 bars. That makes sense? Okay, so let's go and look at my Excel. So if I, let me see if I can copy this whole lot. The picture looks the same as before, except that this value here is now not 0.3, but 0.3 divided by the square root of 4. Okay, and this one is divided by the square root of 4, because I'm now dealing with 4 bars. So instead of this formula, I now don't have 0.3, but I have 0.3 divided by the square root. So can you see that my probability has now increased to 0.90876? Let's see if that's the answer they got. Man, look at that. Okay, I don't know how they got 0.908. But anyway, there. Can you see? Again, I don't have to normalize or anything if I use Excel. So graphically, if you just draw 1 chocolate, the sample size is 1. And if you draw 4, the chocolate size is, the probability is getting much higher. And this is because we're using a normal distribution that in the first case is sort of quite wide, and in the last case is quite narrow because the sample size increased. Any questions? This whole inference thing, it sort of breaks one's brain a bit, huh? But all I can say is, if you work through a number of examples, unfortunately, we're in applying statistics. We're not in trying mathematically to prove how it works. We just apply it statistically. Okay, shall I do the next one? You first want the break to think about it, or shall we carry on? I'm going to need a break just now. I think let's break here. I'm just going to copy it so long into my Excel. Plus Control V. And then we're going to follow exactly the same process to do this one. You should now see the pattern. Okay, let's break for 5 minutes, and then we're back.
Will you still send out the links to these recordings?
Yeah. And we're recording. Okay, let me just see. I'm going to pause the recording.
Turn off the video. Mic's off. This is a cool one.
Okay, are you guys seeing my screen?
Yep.
So let's walk through this example. What's the first thing we do when we see something like this? We draw. Okay. We know it's a normal distribution, so we draw it. Just a rough sketch. And obviously, if you've got a piece of paper, it's much simpler to draw it on a piece of paper. I just got to do it now so that you guys can see what I'm talking about.
Mm.
And draw this axis. Okay. Okay, the average weekly income of graduates 1 year after graduation is $600. So this is 600. Right. Suppose the expression is normally distributed with standard deviation of 100. So roughly around here is equal 600 plus 3 times 100. Okay. No, wrong. Plus. And over here is equal 600.
Oh, was that 600 plus 300?
Minus 3 times 300. Okay, so let's just see standard deviation is 300 and average is 600. I lie, this is just 100. Okay, so now here's our picture. What is the probability that 25 randomly selected graduates have an average weekly income of less than $550? So we now know less than $550. So we draw the line. 550 is about there, right? 550. 550. Okay. And we now interested in which area? We're interested in this area here. We're interested in this area here. Okay. Now, they say here that 25 people are randomly selected. So we now know the standard deviation for this 25 people is actually not 100. It's divided by the square root of 25. Remember? So for 25 people, the standard deviation is, and it's now equal 100 divided by the square root of 25. Right? So now I can do my probability. I'll just do it like this. Probability of X less than 550. And it's the norm dist. Okay, now all I have to do is fill in the stuff. 550, comma, what was the mean? 600. What was the standard deviation? 20 and true. Now, before I display the answer, I quickly check. I expect it to be in the region of 0.4, less than 0.5. You understand that? Let's see. This is too small. Looks too small to me, 550. Okay, no, it's right. Because in this particular case, this is not 300, this should be 220 for this example. And this should be plus 20. Can you see that this distribution is actually very narrow? So this portion here is a very small, so this whole line need to be there, and this whole thing need to be much smaller. Do you understand why I say that? If you think about it, 550 is actually very close to that amount there. Can you see how the drawing helps me? So yes, now I accept that is actually quite small. Okay. Okay, then it asks the next question. If a random sample of 25 students actually had an average weekly income of 550, what would you conclude about the validity of the claim that the average weekly income is 600? Again, the probability will be small, isn't it? If I actually say that it's so far away from 600, I would be skeptical about that conclusion. So let's go and see what they say in the example. In the actual thing. Right, let's see if they got the same answers I did. Okay, let's X be the weekly income, X normal distribute, and N is, N is 25. I worked on an N of 20, did I?
Yeah.
Okay, so N is actually 25. I'll go and change it just now. X is 600, 100 divided by square root of 25, and X is normally distributed. We want to find this, come up with 0.0062. Let's go and change my calculations. Oh no, I did use 25. Oh, I did get to the same answer too. How cool is that? Okay. But I didn't need to do this normalization and stuff that they've done and look it up on tables because I use Excel. And I recommend you use Excel too. With me, the probability of having a sample of me is very low. So the claim that the average weekly income is probably unjustified. My word was I'll be skeptical. It would be more reasonable to assume that me is smaller than 600 because then the sample becomes more probable. Okay? Can you see how you can, they said to me the average income is 600, but I won't get a sample of 25 people with that low. The probability of that is very small. Okay. Creating the sample distribution by computer simulation. Did any of you by any chance manage to get the book? When you purchase the book, you can download the seeing statistics applets and stuff. I couldn't get it to work, so I've not used that, but I've used Excel. Let's just see how we're doing for time. 7:41. Yeah. Okay. At any rate, if you simulate it, this is what you would get. We can go and simulation of a dice tossing. If you've got 2 dice, 5 dice, or 10 dice. Let's just see what else they're dealing with here. Okay. I'm going to simulate this for you in Excel. How cool would that be, huh? Do you think that's even possible? Okay. You think, how will I do it? My big mouth. Okay. Say for instance, I take a dice and I throw it once, and I need to get a random number in rand between 1 and 6. So that gives me a random number between, and if I do it now, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, but let's start off, and I just, okay, yeah. Okay, if I draw 10 samples of 1, and I calculate equal the mean of this, I expect it to be roughly 3.5. Okay, not mean, the average. Okay, I said it will be near 3 point. So if I press F9, it will actually redo the whole thing. Then I get 4.4, 3.7, 2 points, and so on and so on. That's if I've done it 10 times. That's what I expect. But what if I insert, if I do this lots of times, and I calculate this lots of times, and I now calculate the average of this, what do you expect will that be? Look how close to 3.5 it is. And you can see I can redo the whole thing, and it will be very, very close to 3.5. Can you see that?
Yep.
Okay. If I also, okay, let's call this average. I'm going to do it now many, many more times. And then I'm going to draw a histogram of all these averages. So how do I draw a histogram? I insert pivot table. Okay. Drag the average there, and average there, count it. What do you expect is going to happen? Let's group it from 1 to 6 by 1. Boom. And if I insert histogram, well, did I do that by 1? No. But can you see that it's sort of a normal distribution?
Yep.
Okay. It's a crude, but there it is. And I can, let's do this plenty more times. I mean, in fact, what I'm going to do is I'm actually going to make this just this 2 sample size. So I'm going to delete all of this. You've seen how narrow that one is. It was very close to there. Now I've just got 2. And if I now, okay, and I'm going to draw many more. insert to the table. Okay. And can you see now it goes to 6, from 1 to 6, because we've just got 2 dice now. And you'll see it's now much more spread out. If I draw a histogram here. You see it's much more spread out, but it's still here. It's still normal distribution.
Normal.
So we can actually simulate all of these graphs by using exactly that technique that I just used now. Okay. Sometimes, and you've seen me often, we've just got a proportion. If we've got nominal data, so up to now we've dealt with numerical data, but if we've got nominal data, the example I had are these beads that I've shown you from time to time. Let me stop the share. I've shown you this box of beads. Now, if I want to estimate what is the proportion of red bead to white bead, I can again vary the sample size. In this particular case, where am I there? Did I lose you guys?
Just in the DOM.
Okay, there.
Yeah.
Okay.
Yeah.
So if I draw with this paddle, I can effectively,
Yep.
This draws 50 beads, and I can count the number of red beads, and I can calculate the proportion. So if you think of proportion, this is a good example to imagine. But we can draw a sample and calculate the proportion. For instance, students at Alpha Crucis, what's the proportion of male to female? Are there more males or more females and so on? So you can always want to estimate the proportion. Again, you can draw a sample and so on. What is the particular thing? The fortunate thing for us, the estimated sample, the estimation of the proportion in the sample is the same as the actual proportion in the population. So if I know that 20% of this,
Yep.
20% of this is, then I would expect roughly 10 out of the 50 will always be that. So let me share this screen again. You can see where I'm at. Okay. So first of all, the estimated proportion is the same as the population one. And then here's the calculation for the standard deviation. Remember the previous time we divided it by the square root of n. In this case, we multiply p, which is the probability of a red bead, and q is 1 minus p. Okay? Divide by that. So that gives me the standard deviation. So I can then again use the normal distribution to estimate stuff. Okay, so we try this one in Excel.
Yes, please.
Okay. Okay, I'm just gonna first look at what solution they come up with. Okay, the number of respondents who prefer Laurier is binomial, the proportion is that. It is normal with a standard deviation of 0.3 and standard error of that calculation, hence the probability of it. Okay, let's go 0.0838. Let me go to my Excel. Okay. So we know that the mean or the proportion is 30%. Okay. Or the number of people that we ask is 1,000. Okay. In sampling, you make the N always small. What is the probability that more than 32 of the respondents say they prefer? So if you hear more than, it always means 1 minus.
Yeah.
I think there's in fact a binomial distribution which I can use. So let's see. Numbers, trials. What would number S be? Let's see. Okay, trials is 1,000. Probability is that calculation, and then cumulative. What would numbers be?
Because you use a binomial test?
Yeah, binomial distribution.
Okay.
Okay, let me just think of it. Number. Okay. Okay, if you get stuck like this, it's always a good idea to go here. Okay, and then it will normally tell me is the number of successes in a trial. Okay. Okay. Okay, this is working the opposite way. So let's just look at norm dist by norm inverse, this one. Let's see if that tells me. Number of trials is 1,000. Okay. The probability is 30%, 0.3. No, this is doing something else. No. Okay. Let's go look at the solution they've given. Okay. That is a normal. Okay, they use the normal distribution. Okay. PQ divided by N. Okay. Okay. Sorry, use the normal distribution. So PQ divided by N. Okay. P is 0.3. Q is 0.7. Do you see where I get that? Divide by 1,000. Okay. Just put an equal sign in front. And now I draw my normal thingy again. So what they've done is they use that law of what was it called? Law of big numbers, I call it something else. I'll think of it just now. get better at this, huh? Insert. Insert. Oops. Okay. So what they say is there's 32%. No, sorry, 30%. And what's the probability that I've got 32%? More, so I'm interested in this area around here. So I'm interested in this area here. Okay.
Yep.
So I'm just now putting in my normal. I need norm list. Okay. Okay, 1,000. No. What do I do for X? Okay, I think it's 32%. The 32% goes in there. The mean is what's in the population. The standard deviation is 0.12321. And this is true. Okay, so I'm getting a big number, and I know I'm expecting a small number, isn't it? So it's 1 minus that.
Mhm.
And let's give it some more decimals. Still work out a very small number, which is because this one is so small. Let's just go and see what they say. Square root of PQ divided by N. Square root of that. Okay. Yeah, now we're cooking with gas again. Instead of that number, I want that number. No, still doesn't work. Normal distribution, 32. No. Okay, I might have to take a rain check on this one. Let's just see again. Okay, I'll have to relook at this one and work it out. Okay, anyway, in chapter 7 and 8, we introduced probability distributions, which allowed us to make probability statements. And the prerequisite of this calculation is a knowledge of the distribution. So at the moment, for everything we've done, we need to know what the population look like. But now, what if we don't know what the population look like? And then we're going to go to compute the probability. Okay, we haven't done that, but don't worry about it. Okay, knowledge of the population and its parameters allow us to do a probability distribution. And we've now developed some sampling distributions. And in the rest of this chapter, we're going to basically cut ourselves loose and say, what if we know nothing of the population? If you think of these beads of mine, you know, if you say, I don't know how many red beads are there and how many white beads are there, but I can sample. And from that sample, how do I draw conclusions? Now, making the assumption of normal distribution and some of the other things which I try to show you in this, we can actually say something about a population, even if we know nothing of that population, by doing some clever maths around it. You see, we've still got a little bit of time, so let me go and figure this one out. Standard error is normal with the mean of this. This should work. Let's see. Must be making a mistake somewhere. Okay. No. Okay. 32. Yes. That's the mean. That's the standard deviation. We always use true, don't we? I can really not see. We've considered 1,000 because we divided there by 1,000. I'm just going to take the one off. So that's not minus. Can anyone see where the mistake is or not?
No.
Okay, that's just the standard deviation is that. Normal with 3. Oh man. Okay, I'll have to come back to you on that. Okay. What any particular questions? I hope it's sort of clear where we go from a population to a sample, and the sample, there's certain relationships with whenever you draw a sample with the mean. The only thing we worry about now is the mean or the average and the standard deviation. And for each of these different scenarios, you can do a calculation. And you basically just need to remember how do you estimate the standard deviation and how do you estimate if it's a binomial distribution, and how do you do it when it's a normal distribution. In the one case you divide by the square root of n, in the other case you do this calculation. But I'll have to look at this some more and come back. I don't know where I've made the mistake. And now this is all recorded. And it can go into eternity with my not being able to figure this out. Anyway, that's life.
Yeah.
Okay, so I'll see you next week if I don't see you before. And,
Thank you.
start working on your assignment,
Mhm.
and I'll try and write up a good assignment. Okay.
Thank you.
Okay. Well,
As well.
anyone else have a question or something? You okay, Sharma? Okay. All the best. See you next week.
See you. Have a good night.
You too. Bye.
Bye.
Bye.